Hello everyone! This video is going to focus on Markov and Chebyshev inequalities. These inequalities have some great uses in statistics, and to start off, we can use expectations of random variables to form conclusions about probabilities of other events for that variable using these inequalities. And these are great too because we don't have to know the distribution. But we do need our variables to be random variables, non-negative or greater than 0, and finite, with finite expectations. All right, we're going to start off talking about Markov's inequality, which is kind of funny because he was the student of Chebyshev. Anyway, so the principle behind it is we take a non-negative random variable x. If the expected value is small, the probability of obtaining a large value is small as well. So the inequality states that the probability of x, the variable x, being greater than or equal to a is less than or equal to the expected divided by a. A is a non-negative constant here. So let's take, and we're going to demonstrate this with the variable y. So y is equal to 0 if x is less than a, but if x is greater than or equal to a, it's 1. So it looks like this a little bit, but this should be an open circle here. There we go. This is apparently a step function. Nice little graphic to see how things are. So let's take this. If we look at this, we know that y is always going to be less than x. Now, because y is always going to be less than x, the expected of y is also going to be less than the expected of x. The next thing that we can do is we can use the definition for the expectation of y, specifically that a times the probability of x being greater than or equal to a is equivalent to the expectation of y. So we can put that in place of the expectation of y. We divide by a, and boom, we have Markov's inequality. All right, for the second method of proving Markov's inequality, got some hints out, but we're going to be using the integration method and the definition of the expectation. So again, we've got Markov's inequality there. And if we look at the definition for the expectation of a random variable, because it's non-negative, we're looking at the integration of 0 to infinity of x times the function. So if we take a number line, we're just going this way, right? We're integrating and we have all of this area there. Now we've got some random a, some constant, and that is going to be less than or equal to a, the integration of a to infinity of x times that indicator function. Now in this instance, we can also treat a as a constant. So we can integrate from a to infinity of a times that indicator function. Because it is a constant, we can bring it out in front of the integration. And we take this definition here, and we can say that that is the definition that the probability of the random variable x being greater than or equal to a. So we can put that back into the inequality, and then again the last step, just like last time, is just to divide by that a. And we have Markov's inequality. All right, moving right along, we're going to focus on Chebyshev's inequality. And again, we've got some hints that we'll fill in later. Now, Chebyshev's inequality focuses on random variables with finite mean mu and variance of sigma squared. Chebyshev's inequality is a little bit different because it focuses on the variance. And it says if the variance is small, x is unlikely to fall from the mean. Now it's a little bit different. The probability of x minus mu, that probability is greater than or equal to c, and then that whole thing is less than or equal to sigma squared over c squared for all, again, non-negative c. And we're going to be applying the Markov rule, the Markov inequality here, so that's why we've got it. Now let's think about what it would look like if there was a small variance. Here we've got a pretty tight bell curve for a distribution. And if our expected value is small, it's not going to be very likely that we have a large value. In fact, it's going to be far from the mean. So let's jump into this proof. We take the probability of x minus mu, sorry, the absolute value of x minus mu, being greater than or equal to c. Now, if we square both sides of that, the inequality will still hold. It will still be true. So if we get that the probability of random variable x minus mu squared is greater than or equal to c squared. Now, this means that it is non-negative and we can apply Markov's inequality here. So if we apply Markov's inequality, we get that the expectation of x minus mu squared over c squared. From here, we can just apply the definition of variance, and we get sigma squared over c squared, which is Chebyshev's inequality. All right, now we're on to the second method for Chebyshev's inequality. And we've got some hints up here, but just as a reminder, here are our formulas. The first being Chebyshev's inequality, where we're looking at variance, and then we're going to look at Markov's. And I like this method too because last time we ended with Markov's, but this time we're going to begin with it. So in the definition for Markov's inequality, we have some random variable x. But if we look at x minus mu as also a random variable, we can treat it as such. So we put x minus mu in for x in the Markov inequality. Now we're going to do the same thing where we square because the relationship in that inequality will still hold if we square it. We're going to then apply the definition for variance, where the expectation of x minus mu squared is the variance, or sigma squared. And again, we have then shown another way to prove Chebyshev's inequality. All right, now just as a reminder, these are the formulas that we use for this slide, and as I make these videos, I'm going to do my best to keep the formulas at the end as a reference. Sometimes it can be difficult to keep everything straight, but on the next video, we're going to be focusing on the weak law of large numbers, and having an understanding of Markov and Chebyshev's inequalities will help us with that.